Okay, good morning. Ready to start? Ali or Rafiq, can you confirm if you can see the screen?
Yes, sir, we can see the screen.
Great, thank you. Thank you very much. Okay, last time we started with, or we finished the class with an example of a queuing system. And this kind of a queuing system is very common in practical situations. So we have a queue, and you have every unit of time, you have arrival, and the probability of arrival or the arrival rate is 1/40. And then there is a server here, and the server is serving the arrivals. So it could be the customers in a bank, or it could be the packets arriving at a network card, and the network card will process those packets and will send those to the applications. Okay. So there is a processing rate, and the processing rate is 1/30. 1/30. Also every unit of time, every time unit. So in one time unit, you have one arrival. You cannot have more than one arrival, and at most one departure. At most one departure. Okay. So what happens? What happens if there is one arrival, okay, and it is still being processed? Because the probability that you will process it is 1/30, there is no guarantee that you will be able to process it in that time slot. So it might so happen that this queue will build up. This queue will build up and will empty out with time. Will empty out with time. So you can see that the arrival rate, which is P, is smaller than the departure rate, which is Q. So this is a queue which will be a stable queue, which means it will not grow infinitely. ये infinitely grow नहीं करेगी. So last time we did some analysis of this queue. We represented this as an infinite state Markov chain, discrete time Markov chain, infinite state discrete time Markov chain, DTMC. Okay, so each state in that discrete time Markov chain represents the number of jobs in the queue, or number of packets in the queue, or number of customers in the queue. Okay, we computed the probabilities of being in each of the state. So you have state 1, state 2. So nobody is waiting, queue is empty, 1% waiting, 2% waiting, and so on and so forth. So on and so forth. So you can see that this is an infinite size queue, although it will not grow indefinitely. So there is a probability that you will go from state 0 to state 1, which means no packet waiting or no job waiting to one job waiting, and probability that you might come back to this state. It's also possible that when there is one packet waiting, one new packet arrives and one packet leaves in that time slot, and you are still waiting in that state. Similarly here, and similarly here. And we saw all of these probability. With probability R, you increase the size of the queue by 1 unit. With probability S, you decrease the size of the queue with 1 unit. So that means 1 minus R minus S is the probability you maintain the size of the queue. You maintain the size of the queue. And R is the probability that you have arrival and no departure. One arrival, no departure. It's the probability of one arrival and no departure. Only then you increase the size of the queue. तभी बढ़ा सकते हैं. Yeah. So R is equal to one arrival and no departure, one arrival and no departure. And this is basically 1 over 40 into 1 minus 1 over 30 will turn out to be 29 over 100. So with probability 29 over 100, you increase the size of the queue by 1 unit. Okay. Similarly, we defined S as one departure, no arrival. Only then you can decrease the size of the queue. Only then you can decrease the size of the queue. So this would be equal to Q 1 minus P and will turn out to be equal to 39 over, should be 1200. Oops. So somehow this pencil has got stuck, unable to write. Okay, this might require resetting. Okay, worked. Became unresponsive for a little bit. 39 over 1200. 39 over 1200. And of course, the probability that you stay in the same state, is 1 minus the sum of these two guys. 1 minus the sum of these two guys. And last time we said that the probability transition matrix for this is infinite size. So not easy to solve it, but luckily it's a tri-diagonal matrix, but tri-diagonal. So still not, although the size is infinite, still not too difficult to solve. Lots and lots of zeros in there. And we can use the symmetry in the structure of P to solve for it. And we last time tried to solve for stationary distribution, and the stationary distribution is pi 0, pi 1, dot, 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 all the way up to infinity is times P is equal to, we are looking to solve for this stationary distribution. Okay, जिसको probability transition matrix से आप multiply करें and you get the same answer. So that's how we define the stationary distribution. And then we solve for, by using the symmetry in P, we solve for all of these pi's, pi 0, pi 1, pi, etc. And then it turned out that pi 0 was equal to 1 minus rho, where rho we had defined to be equal to R over S. And has to be less than 1. You cannot solve this if R over S is equal to or greater than 1. You will not be able to solve this. If R over S is greater than 1, then you will notice that if R over S is greater than 1, you are increasing the size of the queue. Your arrival rate is faster than the departure rate. So that means this would be a queue. If R over S is greater than 1, it would be a queue whose size will increase indefinitely. So by using R over S less than 1 and defining it to be equal to rho, we found that pi naught, the probability that you will find yourself in state 0 is 1 minus rho, Okay. And pi I for any other guy, pi I in general would be equal to rho power I. Also true for pi naught, but yeah. So this is what we found. This is what we found last time. Okay. So a pertinent question about this is, one might be interested in a practical situation. What is the average queue size? So देखें यहाँ पे packets arrive होते जाते हैं हर time slot में and depart होते जाते हैं हर time slot में. But both of those things, arrival and departures, are happening with certain probabilities. Okay, and the arrival rate is slower than the departure rate. This P is less than Q. Okay, So what is the average queue size? I'm interested in finding out that in a single server queue at a bank, if you have a customer queue, what is the average size of the customers? If the customers are arriving with certain rate, departing with some certain rate, and the bank teller is taking certain time to serve a customer. So a very important question, very practical question is to find out how many people in the queue on average, how many people in the queue on average. Okay. So relevant question is to find the average queue size. Average queue size. So pi zero is the probability. Pi zero is the probability. If you look at this Markov chain, then pi zero is the probability you will find yourself in state zero. Pi one is the probability you will find in yourself in state one. Okay. So you can see that these, since rho is less than one, so increasing of occupancy, the probability of increasing occupancy, these are decreasing. Pi zero is the highest, pi one is smaller, pi two is further smaller, pi three is even smaller, and so on and so forth. So that means the increasing queue sizes are decreasingly probable. Okay. And I'm interested in the average queue size. So average queue size, let n is the queue size. I'm interested in expected value of n. And you can intuitively see that n should be dependent upon the interaction between the arrivals and departures. Okay. So what is n? N is zero. The queue size is zero with certain probability, and that probability is pi naught, that you find the Markov chain in state zero. उस वक्त उसकी queue की जो length है वो zero है. You find the Markov chain in state one, which means queue length of 1 with probability pi 1, 2, pi 2, and so on and so forth. Okay. So expected value of n would be equal to, so 0 into pi naught, 1 into pi 1, which is rho into 1 minus rho, plus 2 pi 2 would be rho square into 1 minus rho, plus 3 rho cube into 1 minus rho, plus so on. So this would turn out to be equal to rho into 1 minus rho. You can take it common outside. So this would be equal to 1 plus 2 rho plus 3 rho square plus 4 rho cube plus so on. And this is a series that you can add with some trick. There are many different ways of solving this. One easy way to solve this is to realize that this is basically the derivative. बहुत सारे तरीके हैं इसको solve करने के. This is just a derivative of 1 plus rho square plus rho cube plus so on. ये देखें इसका डेरिवेटिव है. इसका डेरिवेटिव 0 आ जाएगा, इसका डेरिवेटिव 1 आएगा, so इसका डेरिवेटिव ये 1 आ जाएगा, इसका डेरिवेटिव 2 rho आ जाएगा, and so on and so forth. Okay, so this is equal to rho into 1 minus rho d by d rho of, what is this guy? This is a geometric series, and infinite geometric series with ratio which is smaller than 1, rho is smaller than 1, and the ratio is rho. So this would be equal to the first term over 1 minus rho. So the derivative of this guy. And this really is equal to, इसका derivative लें and you solve it, you end up getting rho over 1 minus rho. That's the expected queue size, So हमारे parameters के लिए solve करते हैं इसको कि you have P is equal to 140 and Q is equal to 1/30. Okay. So P is equal to 140, Q is equal to 1/30. इससे हमारे पास R क्या आया था? R was 29/1200 and S was 39/1200. So this gave us R is equal to 29/1200 and S is 39/1200. Okay. So expected value of N would be equal to, what would be rho? Rho would be equal to R over S. R over S, which is 29/39. Okay. And you can see that this is less than 1. So this would be 29/39 divided by 1 minus 29/39 turns out to be 2.9, the average queue size. Of course, if I increase the arrival rate, if I increase P, then I should expect an increase in the average queue size. If I increase Q, the departure rate, if I increase the departure rate, I should expect a decrease in the average queue size. And you can put those values and you can play with those values and find those out. Okay. So now I'm going to move to a few definitions and theorems. Few definitions and theorems. So last time we talked about irreducible chains theorem. So a regular Markov chain, regular means that it is irreducible, which means every state communicates with every other state. All the states communicate with each other. And what do we mean by communicate? That means with non-zero probability, you can go from one state to any other state. हमने एग्जांपल देखी हैं ऐसी चेन की जिसमें एक स्टेट से बाहर निकल गए तो फिर there is no way to come back to that. That kind of a Markov chain will not be irreducible. So a regular Markov chain which is irreducible and aperiodic, irreducible and aperiodic, which means कि उसका period जो है हर state का वो 1 है. Finite state, a regular Markov chain with finite state has a limiting distribution, ये हमने last time भी establish किया था, as a limiting distribution also equal to, that limiting distribution also equal to the stationary distribution. And what were those? Stationary distribution is the distribution, probability distribution of being in different states, and you start with that, or Markov chain को आप एक step आगे ले जाएं तो the state remains the same. So that means stationary distribution क्या होती है कि pi times p will be equal to p pi. So this is your stationary distribution. And what is a limiting distribution? Limiting distribution is the distribution that you will eventually get. Starting from any distribution. You can start, of course, start from the stationary distribution. तो बस आपको जो है वो start से ही जो है वो limiting distribution मिल गई है. लेकिन limiting distribution क्या है? Limiting distribution is the one that you start in any distribution. And you stay in the Markov chain long enough. Start with any distribution. Okay. So limiting distribution क्या है? Start in any distribution. P1 or P0, P1 dot, 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 etc. Start with any distribution and then stay here for a long enough time, p power n with very large, n very large, going to infinity, then you will end up getting this limiting distribution. Limiting distribution. And at that time, when you have p power n for very, very large n, all the rows of p will be exactly the same. And each of those rows is actually telling you this limiting distribution. So the theorem is that every irreducible and aperiodic, which means a regular Markov chain, finite state Markov chain, has a limiting distribution that is also stationary. So what about infinite state DTMC? What about, ये अभी हमने ऊपर एग्जांपल देखी है. What about infinite state DTMC? अगर Markov chain जो है वो infinite state हो, so will this theorem still apply? Well, it seems that this theorem still applies, but we also need the Markov chain to be what we call positive recurrent. इसका क्या मतलब है positive recurrent का? We talked about the recurrent states. Recurrent states are the one जहां पे आप बार बार वापस आते हैं recurrent states में. ठीक है? So I will give you an example of what we mean by positive recurrent. Okay, but we need to wait for that for a minute. Okay. So what about the mean times between visits to the states? Before we do that, I'm going to define what we call hitting times. What is a hitting time? So hitting time is the time that you first time hit a state starting from any other state. Okay. So starting from state j not equal to I, how long does it take to visit state I on average? And for the first time. Okay. And I call this Mij. It's the expected number of times steps needed to first get to state j starting from I. Okay. And then I also define what we call return times. Return times means you start from a state and you come back to the same state. Okay. So MII is the return time for state I. And average value. This is an average value. Okay. So it's also the expected number of time steps needed to come back to state I, starting from state I. Starting from state I. There are multiple ways of calculating the mean hitting times and mean return times. Okay. We will give you a couple of examples for that. Okay. So one thing is it can be shown is that for an irreducible finite state discrete time Markov chain, okay, MII is finite. MII is finite, which means you will always come back to this state after a certain period of time, not after infinite time, but less than infinite time. We can also show that, this is another theorem, we can also show that MII is equal to 1 over pi I, 1 over pi I, where pi I is from the stationary distribution. Now, this makes a little bit of sense as well, intuitive sense. This makes a little bit of intuitive sense. Okay, dekhiye, pi I is the probability of finding yourself in state I. If you find yourself in state I very frequently, agar pi I जो है वो बहुत ज़्यादा बड़ा है, so that means कि you should be coming back to that state very quickly. अगर आप एक स्टेट में बार-बार quickly वापस आ रहे हैं, if MII is very small, that means you are coming back to that state very quickly, and that means you are finding yourself in that state very often, which means कि pi I has to be large. So this is a intuitive kind of an expression, but it can be proved as well. It can be proved as well mathematically. And pi I is the stationary distribution, which we had defined to be limit n going to infinity p power n. Okay. This is your probability transition matrix or transition probability matrix. Uska ith and jth element, अगर आप ले लें, all of those will be the same. सारी रोज उसकी, अगर आप p की पावर इनफाइनाइट ले जाते हैं तो सारी रोज उसकी सेम हो जाती हैं, और सारी रोज अगर सेम हो जाती हैं, so that means उसका जो ith element है is pi I. Okay. So I'm going to also talk about what we call time averages. This is the, intuitively this is similar to pi I, but it's a different way of looking at it. Pi I is the probability that you will find when you randomly look at the Markov chain in the steady state. What is the probability you find your Markov chain in state I? That is pi I. Okay. I define time average as Pj is the fraction of time Markov chain spends in state J. State J के अंदर, so and both of those look to be similar. कि जो probability है find करने की in state J and how long you spend in state J, if the time steps are discrete, वो एक unit की हैं सारे. So we will in future we'll be talking about, in the next week we will be talking about the continuous time Markov chains as well. Okay. In the continuous time Markov chain, you move from one state to another after some random amount of time. So ऐसे नहीं होता. Discrete time के अंदर you move from one state to another state at discrete times. T is equal to 1 or n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, like this. But in the case of continuous time Markov chain, you might be spending a long time in one state and a short time in another state. Okay, so so the transitions will be happening at random times, but in discrete time Markov chain, the transitions are happening at discrete times, fixed time step के बाद हो रही है. So continuous time may this pi I might not be the same as Pj, but for the discrete time Markov chain, Pj is the same as pi j. Pj is the same as pi j. The probability of finding your Markov chain in state j is the same as the fraction of time the Markov chain will spend in state j. Okay. So I'm just going to give you a very quick example of an infinite state DTMC. Infinite state DTMC. So we said that for finite state DTMC, the limiting distribution exists if the Markov chain is regular. That means it's irreducible and aperiodic. For infinite state Markov chain, discrete time Markov chain, I also want the Markov chain to be positive recurrent. Okay. And to define that, let's consider the arrival and departure rates of the FIFO queue, first in first out queue that we studied earlier. ये जो हमारे पास customers in a bank आने वाला जो था कि at certain rate they are arriving, certain rate they are being served. Okay, so let's try to relate with that. So you are in state 0, you are in state 1, you are in state 2, and then so on and so forth. This is an infinite state Markov chain, infinite state Markov chain. With certain probability, you stay back in 0. With certain probability, you increase the size of the queue. And certain probability, you decrease the size of the queue. With certain probability, you stay in the same state, which means maintain the size of the queue. Okay. So ये इस तरह के आपके पास एक chain बन जाएगी. So I'm going to make a copy of this chain to give you an example कि positive recurrence का क्या मतलब है. Now, if we considered this chain, यहाँ पे हमने कहा था कि the chain increases the size. The chain increases the size of the queue by probability R at every time step and decreases the size of the queue by probability S at every time step. Okay. So R को हमने S से small लिया था. Otherwise, we have an infinite kind of a stuff. You know, the queue size will continue on increasing. So I can probably write these probability numbers here. Example दे रहे हैं यहाँ पे hypothetical numbers. So 0.4, 0.4, 0.4, and then we can have 0.5 here and 0.1 here and 0.1 here, 0.1 here. Okay. Now you see the size of the queue increases with lower probability than the size of the queue which decreases with a higher probability. This kind of a infinite state DTMC is called positive recurrent. Positive recurrent. इसको positive recurrent बोलते हैं. If I have 0.4 here and 0.5 up there, with more probability you are increasing the size of the queue, with more probability you are increasing the size of the queue, and less probability you are decreasing the size of the queue. Okay. This kind of a Markov chain, discrete time Markov chain, every state is transient. Every state is transient. There will be a time after which with probability 1 you will never come back to that state. So अगर आप state 2 में अभी हैं, so there will be a time in future after which you will never come back to state 2. Okay, so this kind of a Markov chain has a transient Markov chain. So हमने define भी किया था कि recurrent states होती हैं और transient states होती हैं. Transient states are the one which are visited for a limited number of times, after which they are never visited. And recurrent states are the ones which are visited indefinitely. You have infinite visits to the recurrent states, and you have a finite number of visits, less than infinite number of visits to the transient states. Now there is a corner case here, which is the case of a null recurrent Markov chain. Null recurrent Markov chain, जिसमें आप size increase और decrease same probability के साथ करते हैं, 0 probability के साथ you maintain the size. 0.5, 0.5, and 0.5. Okay. Now this is a very corner case. So recurrent के अंदर you visit the state an infinite number of times. Every state infinite number of times. Transient में you visit every state with a finite number of times. There will be a time after which you will never come back to that state. Okay. Null recurrent के अंदर you will not come back to a state, but you still visit it after a certain number of times, but you still visit the state an infinite number of times. So ये जरा एक corner सा case है, जो समझते हैं. So I'm going to redefine the recurrent and transient states again. Recurrent and transient states. Recurrent and okay. So let Fjj is defined as the probability that a Markov chain starting in J, in state J, ever returns to state J. Ever returns to state J. कभी दोबारा वापस आएगी वो state J में. ठीक है? So definition. If Fj is equal to 1, if there is 100% chance that you will come back to where you are, so that means जब आप वापस आ गए तो एक दफा वापस आ गए तो फिर then there is a 100% chance you will come back again. फिर दोबारा वापस आ गए तो still there is a 100% chance you will come back yet again. Okay, so that means you will have an infinite number of visits if Fjj is equal to 1, and this kind of a state, J is recurrent. And if Fjj is less than 1, then state J is transient. So with probability 1, 100% chance है किस चीज का, कि number of visits to recurrent state is infinite. Okay, and number of visits to transient states is finite, which means that there will be a time after which you will never come back to the transient state. Okay. So for transient state, every time you are in a transient state, ये transient state है. Okay, so let's say this is state J and this is transient. Okay, Fjj is the probability that you will ever come back here. So for this Fjj is less than 1. The probability that you are here and you will go somewhere else and ever come back here. This Fjj. Okay. The Fjj is less than 1. There is less than 100% chance that you will ever come back here. Okay. So that means कि यहाँ से बाहर निकलने का forever के लिए बाहर निकलने का 1 minus Fj is that probability. 1 minus Fjj is the probability. So that means कि the number of visits that you will have here, would be a geometric random variable with parameter 1 minus Fjj. तो geometric random variable, if you recall, वो क्या होता था कि आपको success चाहिए होती है, ठीक है, with some probability p, and success in this case is never coming back to state J. that is success. So this is a geometric random variable. Number of visits to state J would be a geometric random variable. And once you get the success, which means that you have exited state J forever, exited state J forever. So I also have another definition or theorem. In an irreducible Markov chain, irreducible Markov chain, that is all states communicating, all states communicating with each other. Okay? So either all states are recurrent or all are transient, or all are transient. So transient Markov chain के लिए limiting distribution will not exist. जो null recurrent infinite state Markov chain है, उसके लिए भी limiting distribution will not exist. So if I can divide the recurrent state into two cases, recurrent state, for an infinite state discrete time Markov chain, this could be positive recurrent, which means कि indefinitely grow नहीं करती, or it could be null recurrent. It could be null recurrent. It could be null recurrent. So mean time between recurrence, MJJ, starting from state J, you come back to state J next. Mean time कितना उसके लिए लग रहा है is finite. Mean time is finite. For null recurrent, MJJ is infinite, which is kind of funny because the mean time between the visits is infinite, yet the state is visited an infinite number of times. Okay. So once again, if as we said, an extension of this definition in an irreducible Markov chain, all states communicating, either all states are recurrent or all states are transient. This can be specialized. For the case of positive recurrent and null recurrent Markov chains as well. Okay. So definition: if I communicates with J, if state I communicates with state J, then if I is positive recurrent, so is J. So J be positive recurrent. If I is null recurrent, so is J. So J be null recurrent. इसको proof हम जो है वो अभी नहीं दे रहे हैं. We are omitting the proof. So now I'm going to talk about what we call ergodic DTMC. Ergodic DTMC क्या चीज है? Ergodic DTMC कोई नई चीज नहीं है. Ergodic DTMC is the one which is aperiodic, which is irreducible, and also positive recurrent, positive recurrent and positive recurrent. So this is the one जिसके लिए limiting distribution exist करेगी, and the limiting distribution would be the same as the stationary distribution. So I'm going to talk about time averages now. Time averages. So first of all, recall that pi j, the probability you will find the Markov chain in state j in the stationary distribution is equal to limit n going to infinity p I j so power n, pij power n. इसको ऐसे भी लिख सकते हैं कि maybe a better way of writing it is कि आपने पहले उसकी पावर n कर दी और उसका ith jth एलिमेंट ले लिया, बट रिकॉल हमने n स्टेट ट्रांजिशन प्रोबेबिलिटीज भी फाइंड आउट की थी. सो दिस इज लिमिट n गोइंग टू इंफिनिटी p n I j, i से j पे जाने की in n steps. Okay. So time average, as we described before, time average is what fraction of time does the Markov chain spend in state j, state I or state j. ये fractions of time है. So define करते हैं इसको formally define कर देते हैं. Definition को formally define कर देते हैं. Let njt is the number of times Markov chain enters state j by time t. By time t, the Markov chain enters state j njt number of times. Then njt divided by t, limit t going to infinity. This is going to be pj, which is the fraction of time. हम इसको ऐसे define कर रहे हैं, fraction of time the Markov chain spends in state j. Okay, हमने देखा था कि fraction of time the Markov chain spends in state j is the same as the limiting distribution k or the stationary distribution that the Markov chain is found in state j. Okay. For a positive recurrent irreducible Markov chain with probability 1, pj, which is equal to limit t going to infinity njt divided by t is equal to 1 over mjj, which is greater than 0. Okay, and mjj is the average time that you start with state j and come back to state j. Okay, so you need positive recurrence and irreducibility. यहाँ पे aperiodicity is not needed. पीरियोडिक चेन्स जो होंगी उनके अंदर भी ये फॉर्मूला चलेगा. Aperiodicity is not needed. Okay? And the proof comes from the strong law of large numbers and renewal theorem, and we will skip that as well. So that means summary, in summary, for an ergodic DTMC, Pj, the fraction of time you spend in state J is equal to pi j, which is equal to the probability you found the Markov chain in state J is the probability distribution, जो उसकी stationary distribution है उसमें से jth element है, is equal to 1 over mjj, and mjj is the mean time to return back to state J starting from state J, or the mean number of time steps between visits to state J, or mean return time to state J. Okay. So now I'm going to introduce something very interesting. Limiting probabilities as rates in Markov chains. So let's say that pi I is the limiting probability Markov chain is in state I. What that means is कि एक Markov chain start करें, leave it alone for a very long period of time, after which it will be found in one of the states. What is the probability in state I? That's pi I. Okay. Remember, pi is the percentage of time or fraction of time it will spend in state I, which is different, by the way. Although these quantities are the same, but these definitions are different. And these two quantities are the same only for the discrete time Markov chains, which are ergodic. अगर ergodic नहीं होगी, तो time averages or ensemble averages बराबर नहीं होंगी. Okay? So these are time averages, these are ensemble averages, as we call them. So we can also consider pi I. Pi I can be considered as a long run proportion of time. The random process, the Markov chain, is in state I. If the Markov chain is ergodic. So we observe that pi I into Pij is the rate of transition from state I to state J. So when do you transition from I to J? Well, the probability of that is Pij. This is the conditional probability that you transition from I to J, given that you are in I, your next state is J. That's the transition probability. But when you multiply this with pi I, this gives you the notion of the rate. Okay. So what is this quantity? This quantity is basically the fraction of time DTMC is in state I with state J as the next step. So आपने I से J में जाना है. Pi I is the fraction of time that you are in state I. Pi I multiplied by Pij is the fraction of time the DTMC is in state I and will transition to state J. Okay. So let's take a look at very large number of time steps. Okay. So look at large number of time steps. time steps t, then this quantity pi I pij, which is the fraction of the time that you are in state I and will transition to state j, then pi ij times t, this will give you the transitions so many transitions will start in state I and end in state j. T, let's say कि आपके पास 10,000 है, so 10,000 को आप pi I से multiply करेंगे, so that's the fraction of time that out of those 10,000 that you found the Markov chain in state I, और उसको फिर pij से भी multiply करेंगे, so that means you will transition from state I to state j. So pi I multiplied by pij multiplied by t is that total number of transitions that you will make from state I to state j. Okay. Example, pi I can be equal to 1/4. That means you found yourself in state I 25% of the time, and pij could be equal to 1/3. Okay, and t could be 10,000. So 10,000 ka 1/4, you will find yourself in state I, और उसको फिर 1/3 से भी multiply करेंगे, will be the number of transitions out of these 10,000, number of transitions from state I to state j. So if this is the number of transitions, from state I to state j in this time, okay, which implies that pi I pij, ये आपको क्या चीज दे रहा है, इसको अगर टाइम से डिवाइड कर दें, it's the rate of flow from state I to state j, state I से state j में जाने के लिए. Okay. So I'm going to ask this question. So pi I pij, and if I sum this up over all j, is the total rate out of state I. So pi I pi1 is the rate out of I into state 1. So pi I pi1 is the rate from I to 1, and then I to 2, and then I to 3, I to 4, I to j, and so this is the total rate out from state I. So if you have state I here, उससे इधर भी जा रही हैं, इधर भी जा रही हैं, इधर भी जा रही हैं, इधर भी जा रही हैं. So there is certain probability you found yourself in state I multiplied by these transition probabilities of going to state j. So that will give you the rate, flow rate out of state I. Similarly, summation pi I pij, देखें ये same thing है, बिल्कुल exactly the same thing. However, now I sum it up over I. If I sum it up over I, that means you were in state I, and you moved to state j. It's the rate for that. So this is the total rate. Into state j. And this includes self loops. j से अगर j में ठहर रहे हैं तो वो भी included. This includes the self loops. So now recall the stationary equation. the stationarity stationary equation. Stationary equation क्या थी? Stationary equation आपके पास ये थी, no, pi multiplied by p is equal to pi. This was the stationary equation. That's how you solved the distribution. Okay? And in addition to saying कि pi के जितने elements हैं, that should sum up to 1. Okay? So if you look at it, so this pi will have these elements, pi 1, pi 2, और pi 0 से भी शुरू कर सकते हैं, pi 0, pi 1, pi 2, dot, up to, wherever you want to go, multiplied by p11, dot, and this should be equal to pi naught, dot, pi I, dot. So how do you get the ith element here? ये ith element यहाँ पे कैसे आता है कि ये पूरा वेक्टर यहाँ से, this entire vector here, this gets multiplied with the ith column, ठीक है? तो ये पहली वाली चीज पहले के साथ मल्टीप्लाई होती है, प्लस दूसरी वाली चीज दूसरे के साथ, ये सिंपल मैट्रिक्स मल्टीप्लिकेशन, तीसरी वाली चीज तीसरे के साथ, एंड सो ऑन एंड सो फोर्थ, आखिरी वाली चीज आखिरी वाले के साथ मल्टीप्लाई होगी. एंड वंस यू डू दैट, you will get the ith element of the resultant. So that means कि your stationary equation is pi I is equal to, ये हम पहले कर चुके हैं, इसको just एक formally लिख रहे हैं. So this would be equal to summation upon all j, pi j into pji. Okay. So यहाँ जो elements हैं ये pji हैं, और ये जो elements हैं यहाँ पे pij हैं. इसके अंदर pi j and this is pji. इनको sum over all j, you will get pi I. Okay. So simple ये मैट्रिक्स मल्टीप्लिकेशन है, आपने इतने एलिमेंट्स को मल्टीप्लाई कर दिया, ठीक है? But what is this guy? Summation upon all j, pi j into pji. So this is total rate into state I. ये जैसे हमने लिखा है, टोटल रेट इनटू स्टेट j क्या है, I पे सम कर दें और I से j पे चले जाएं, सारे आईओ से j पे चले जाएं. यहाँ पे सारे j से आप I के ऊपर आ रहे हैं. So you have an I here and you have many of these guys coming in. So j and sum over all j, and this rate is the total rate into state I. Okay. Also note that I can write pi I to be equal to pi I summation upon j pij. Why is that? Because this is simply the one row of the probability transition matrix. Okay. और सारी रोज का सम जो होता है वो आपके पास 1 होता है, sum is equal to 1. ये हमेशा 1 होता है, हमें पता है, ठीक है? So this can be written as summation upon j pi I pij. And what is this rate? This is total rate out of state I. So ये आपके पास state I है, dot, ठीक है? So sum over all j pi I, found yourself in state I, and I से J की तरफ जाती हैं, sum over all J. So this is the total rate out of state I. Out of state I. Okay. What that means is कि ये देखेंगे, ये वाला ये भी पाई I के बराबर है, और ये वाला ये भी पाई I के बराबर है, ये भी पाई I के बराबर है. Okay. So pi I is basically summation over all J pi I into Pij, and is equal to summation over J pi J Pji. So this is total rate into sum of all those probabilities or probability rates into state I, and this is total rate out of state I. And this makes sense. And this makes sense. जिस रेट से आपने एक स्टेट के अंदर जाना है, उसी रेट से आपने उस स्टेट से बाहर निकलना है. ठीक है. Otherwise you are saying कि उस स्टेट में you absorb in that state. Otherwise you absorb in that state. So now if we ignore the self loops, if we ignore self loops, अगर self loops को ignore कर देते हैं, ठीक है, I से I में ही जाने वाला जो loop है उसको ignore कर देते हैं, then summation J not equal to I pi I Pij. So ये वाली जो expression है आपके पास, I have just used this expression here, ignoring the self loop. This was the total rate out of state I. So this should be equal to summation, once again, J not equal to I by J Pji. Okay. So ये आप देखें, ये this is the same as this guy here. Once again, ignoring the self loop. Okay. So what we have done here is removed pi I Pii from both sides, from both expressions. And these are called balance equations. The flux inside a node is the same as the flux outside. Flux into is equal to flux out of every node. Okay. And this can also be applied to a single state as well as a group of states. ये group of states को भी apply कर सकते हैं. So I'm going to summarize here what we have studied. Next time we'll talk about the continuous time Markov chain, but the summary is, okay, given ergodicity, and we understand what ergodicity is irreducibility, aperiodicity, as well as for an infinite state Markov chain, this means positive recurrence. Okay? So given ergodicity, there are many equivalent ways of looking at the Markov chain limiting probabilities. Many equivalent ways of looking at Markov chains limiting distribution probabilities, limiting probability distributions. Okay. One is stationary probability for state J. One is stationary probability for state J. Stationary probability for state J, which is pi J, is equal to summation on I pi I Pij. तो इसको कैसे सॉल्व करेंगे? इसको सॉल्व करने के लिए we just write pi j for all j and also include the summation of j pi j is equal to 1 and solve. So this is stationary probability for state j. Also limiting probability for being in state j, and that would be pi j would be equal to limit n going to infinity p power n iska ith jth element, also the same as limit n going to infinity p I j iska nth. ये n स्टेप ट्रांजिशन प्रोबेबिलिटी से देख लेंगे, या प्रोबेबिलिटी ट्रांजिशन मैट्रिक्स की n पावर ले लें और उसका फिर ith jth एलिमेंट देख लें. both of those are equal. Third way of looking at it is by looking at the reciprocal of mean return times. So pi j would be equal to 1 over mjj. Starting from state j, on average, how long does it take to come back to state j? Okay. And last is look at the time averages. Okay, which is the fraction of time spent in state j. And that would be pi j would be equal to limit t going to infinity njt divided by t, which is equal to pj, where njt is the number of times the Markov chain will enter state j by time t. ये हमने njt पहले define कर दिया. Okay. So this finishes our discussion of discrete time Markov chain. Next lecture we will start talking about the continuous time Markov chain. Discrete time Markov chain mein there is a lot of other important stuff that we may need to look at, but हमने 2-3 ही examples इसकी देखी हैं. एक queuing system हमने देख लिया कि you have discrete arrivals and discrete departures. So average queue size उसमें हमने निकाल लिया. We had also looked at the Google's PageRank algorithm. So you can use the discrete time Markov chain to model the PageRank system in a search engine. So ये दो हमने important examples इनकी देखी हैं. And then we looked at the flux rates into and out of the states आज के lecture में. And then you know there is a lot more theory of discrete time Markov chains that obviously we will not have the time to cover, but we will start with the continuous time Markov chains as an extension of a discrete time Markov chain. So continuous time Markov chain में ये होगा कि you transition from one state to another state, लेकिन discrete times के ऊपर नहीं कर रहे होंगे. It will be a random amount of time that you will be spending in state I before you move to state J. Again. So we'll take care of that in the next lecture or next week. It seems that the next week would be the last week for the classes, and we have just 2 more lectures. I think it would be sufficient to cover the continuous time Markov chain and maybe review some of the material. Okay. So if there are any questions before we close the session, we will be happy to answer.
Sir, will you upload these notes on the LMS?
ये notes अभी मैंने बनाए नहीं है, ये क्लास के notes ही हैं, ये तो वीडियो के अंदर आ ही जाते हैं. But I have not finished making the notes जो normally हम upload करते हैं. So as soon as I do that, I will be able to upload those notes. मुझे पता नहीं है वो कब होगा, 1 दिन में होगा, 2 दिन में होगा, 5 दिन में होगा, but I will upload at least some of the notes. Okay. Any other question? कोई और question हो? All right, then I'm going to stop the share and close the session. Thank you very much for showing up in the morning.